Let's start, and thank you and welcome to the second session like my lecture on theoretical, experimental and computational techniques in soft active material. Yesterday I have shown you that how the different external stimulation can be used for the actuation purpose. Then we have specifically focused on electrical stimulation, where we have discussed about the dielectric elastomer, and we have taken it to the advanced application in minimum energy structures. And we have seen that with the help of minimum energy structure made up of dielectric elastomer, we can basically develop the different types of devices or application oriented things that is implemented in soft robotics application. Now the concern is that I am always telling you the third part, H, how. I am always telling you that please focus on the 3-word principle, WWH, what, why. We understand that what is soft active material, specifically dielectric elastomer. Then we understand what is dielectric elastomer based minimum energy structure. But the concern is we have seen the formulation, basic formulation, analytical modeling, experimental characterization I have also shown you, okay. And at last I have shown you that how we can take it to the finite element. So there is a specific reason for each and everything. Analytical modeling is required because we can get the exact solution, okay. But the problem is for the complex geometry, it's not possible to get the analytical solution. Already Professor Prashant Saxena has told you, whenever the problem is complicated, it's not easy to solve that. The reason is you can't get the basic governing equation of the motion of the actuator. If it is very, very complicated, it's made up of complicated shape, okay. Second thing, we have seen that carried out experiment is one of the best way, but it is always not feasible. There are many reasons, like the availability of the materials, okay, cost, time consuming, because carrying out one experiment is not that much easy. I can show you today. You have to prepare everything in an accurate manner, otherwise there will be a lot of error will creep in. For example, if you are putting carbon grease, okay, manually, definitely you are not going to put it uniformly, okay. So there is a chance that lot of error will creep in. Then we have seen that such type of actuator will undergo inhomogeneous deformation. So in analytical modeling, we are not going to take that. We simply assume that it is homogeneous deformation and we derive it, okay. And second thing is finite element model can be used to take this inhomogeneous deformation into account. And the other thing is that for complicated geometries, always numerical techniques are preferred, like finite element, okay. So now to come how to basically have this all techniques that I have discussed, analytical, experimental and finite element. That is the very, very important things, how we have done, and it will be useful for you also, that you can also utilize the same technique or the advanced techniques that you want to propose. But the basic you will get the understanding of the basic, that how we can basically have these 3 modeling techniques for the soft active material. So today's session is entirely based on that. So let's start. So just a quick overview what we have seen. The problem in dielectric elastomer is seen. We have seen that it exhibits strong material non-linearity. We have already discussed. And that material non-linearity basically arises from the inherent properties like viscoelastic behavior. We have seen that dielectric elastomer, specifically acrylic elastomer, it exhibits strong viscoelastic behavior, okay. So that become the one of the cause of the material non-linearity, okay. And also the hyperelastic behavior. For example, some of the elastomer like silicon based elastomer, they are hyperelastic, they don't exhibit that much of viscoelastic behavior, but still hyperelastic will also lead to non-linear behavior. We have already seen the graph that stress strain curve is not going to be a linear one. In the hyperelastic, we are going to have the stress strain relationship. Instead of stress strain, we are having stress stretch relationship. So I am telling you, in the elastomer, we have already discussed like stretch will be taken into account. And it is all nothing, it is strain plus 1. Already we have derived this thing, okay. So this dielectric elastomer exhibits strong material non-linearity, that we are already known that thing. And when we implement that for the minimum energy structure. So minimum energy structure is a combination of dielectric elastomer membrane with the compliant frame. So what is happening? When the combination will come into picture, definitely when the assembling is being there, geometrical non-linearity also creep in. You are getting my point? whenever the geometrical non-linearity will come, so along with the material non-linearity, you have to take into account this geometrical non-linearity for the effective design of DMS based actuator. This thing we have already covered. Okay, and I have told you that it's very, very important while modeling, you have to take both this non-linearity into account. How we have taken? For example, we have taken a viscoelastic behavior by using Jenner rheological model. Okay, and geometrical non-linearity automatically will, in the modeling aspect, when you see that frame bending stiffness will automatically derived in terms of the parameter of the dielectric membrane, like shear modulus, the dimension of the membrane. So they are coupled. So indirectly, if you are basically providing some dimensionless parameter to the frame bending stiffness, you are taking into account the geometrical non-linearity that will automatically get fitted into that, and you solve for that. Okay. So the first one that I believe is the most important one, experimental. So if possible, if feasible, always go for the experimental. Why? Because that is the main thing you are going to implement. In the practical application, first thing is your model at least should work practically. Okay. If you are developing something, okay, that's feasible, that's either modeling wise it's feasible, mathematically you derive, numerically you solve, but if it is not of practical use, then it's really a waste of thing. Okay. So always go for first modeling aspect by experimental characterization. So we have already seen that, I have already bring all the stuff for you here that will help you like in understanding that how we basically fabricate dielectric elastomer based minimum energy structure. I will show you step by step so that online participant can also get the glimpse of that, how we fabricate that thing. Okay. So I have already told you yesterday that our dielectric elastomer based minimum energy structure, it consists of, first thing is what? First thing is what? What is the important thing there initially? Dielectric elastomer membrane. Okay. And that too in the pre-stress state. So if you see here, this is basically the overall different ingredients or the components you require to fabricate a DMS based actuator. So we again start with the very basic. For example, if you want to fabricate bending actuator, simple bending rectangular actuator having a rectangular cross section with the rectangular active area or the rectangular electrode. So what are the ingredients required? First thing that is the most important is dielectric elastomer membrane. So that too in the pre-stress state. Okay. Why? Because when we are defining the dielectric elastomer based minimum energy structure, the first configuration is initial configuration, and that is basically governed by the pre-stretch of the membrane. Because of the pre-stretching, the strain energy will be developed in the membrane, and that basically enforces the bending of the frame, ultimately lead to the minimum energy states, okay, of the entire configuration. So the membrane is required, dielectric elastomer. So basically this is, we are using a VHB membrane. Okay. So VHB here, it's an American company, VHB 3M. VHB stands for very high bond, very strong bond. Okay. So yeah, no problem. So we are discussing about the different techniques, experimental, analytical and computational. Okay. So we have started with the experimental part. So we are showing that the different ingredients that is required to produce this DMS based actuator. Okay. Now first thing is dielectric elastomer based minimum energy structure, in which we are having dielectric elastomer membrane. That is the foremost requirement. Then it is basically, I will show you one by one the different geometrical parameters of this, of VHB membrane. But first we understand what are the components are required. So second thing is what? For DMS, frame is required. So okay. So that frame is basically, this is the frame that we have shown. It is a compliant frame. It is basically made up of PET material. I will show all the material description, geometrical parameter. But first we understand what are the different components we require to fabricate a simple bending actuator made up of DMS. Okay. So second frame is required, and that frame basically, you see geometrically we have to cut it a hollow rectangular section, you can say at a particular location. So why it is required is, can anyone tell? We have already discussed ki we required, yeah. Bending moment is required, ठीक है, but why we are making it hollow? Yeah. So the concern is when you having a pre-stretch membrane, you put it this, you require an active area. For particular active area where carbon grease is going to apply, you require some active region. So across that hollow cross section, you will apply the carbon grease. Okay. That is why it is being produced as a hollow rectangular cross section at the bottom, at the particular location. Okay. Then the carbon grease. It is basically nothing what we are already going to show you. It is a carbon grease basically, that is basically get mixed with some tarpaulin oil to make it less viscous, and then we can apply it on the active area of the minimum energy structure. Okay. So the third part is carbon grease, carbon black you can call. Reinforcement. So I have already give you a glimpse that why we require reinforcement. Can anybody tell why the requirement of stiffener is being come into picture? To avoid warping. The first concern is we have seen that when we develop a simple bending actuator, we require in-plane deformation. We want this type of motion, bending motion only. But what is happening at the tip, we have seen that there is some out of plane deformation like this will be occur. That is undesirable. Where specifically in the application like gripper, if you are having a warping, you can't grip the object in a proper manner. So to avoid the warping, we require to introduce the stiffener, and that stiffeners we are trying to uniformly distribute along the surface of the frame. We have also seen that there are not only stiffeners are used for basically reducing the warping, it can also tune the attained angle of the minimum energy structure. Okay. So I have shown you that how if we are going to vary the spacing, your attained initial angle and the final actuated angle is going to change. So for a particular application, if you want that we want certain angle, so you define the spacing between the consecutive stiffener. And the third thing is, by implementing the stiffener at a particular orientation, what we will get? Sorry? Twisting. So you see when we are designing flapping wing actuator made up of this DMS. So it's not always like that bird will have all this thing, have bending actuation. It will have, along with the bending, it can also have twisting. So for example, if you are designing flapping wing made up of DMS actuator, so you need to orient the stiffener at a particular orientation. So that orientation can be 30, 45, 60, you can going to vary. Initially it will be at a 90 degree. Okay. So you can see along with the bending modes, we will get the twisting modes of deformation, and that is actually, you will see in the practical application if you are biomimic the response of some flapping wings. So you can see, problem arises, we find a solution, and that solution provides a certain advancement in your research area. We initially implement stiffener to avoid warping, but that stiffener we can vary the orientation to get the different application of the flapping wing. Getting my point? So stiffeners is also required. So for basic bending actuator, these ingredients are required. And for advanced application, you see all the ingredient will be the same. Only the shape of the compliant frame that you are using is going to be changed. So that's why I am saying initially we have a concern that people are using, develop simple bending actuator and then club them together or assemble them at a common platform to get different configuration. But that's a very, you can say, crude approach. You cannot develop things like this. As an engineer, you know, whenever the failure will occur, it will be at the intersection or at the joining point. So you are not going to take that risk. So we decide why we are not going to design a compliant frame having a complex shape. That's okay. But at least it will have a uniform distribution of all the things. That will ultimately, if the failure will occur, it will be for the entire structure, not at a particular location, at the assembling point. Okay. So we are going to move ahead. So dielectric elastomer. So please, Keshav, you can come here. So we will show you here for the online participant, and in person we will directly show you here. So the dielectric elastomer is basically, we are using 3M4910. That 3M is your bring? This is Chinese. Okay. So that is basically, I will tell you one distinguished also effect here. So this VHB tape earlier, it is basically used for adhesive purpose. You can see This is earlier is being utilized as an adhesive or basically joining of two or more components. It is an adhesive tape. But people have observed that this tape basically having the property of dielectric. Okay. This says that this exhibit a very strong property of dielectric. So why can't we are going to use it for some dielectric application? From there the approach has come. Initially it is continuously using as an adhesive, and one more good advantage is that when we are using this tape, since it is having adhesive property, you need not to paste anything over the tape and then provide a frame. You directly provide a frame because of its adhesive property, it will get stick to that. Otherwise, I am telling you, when you are using glue in the other type of elastomer, so what is happening? Again, the manual fabrication error will creep in. You are providing a glue. If it is not uniformly distributed, it will not get paste. Frame will not get paste at a particular location, then your instrument or device is not going to work. You are getting my point? So this adhesiveness is an advantageous effect in the VHB tape. So the thing is, I am telling you that it is basically available in 3 different thickness. Okay. So as depending upon the thickness, it's you can say a standard name has been given to them. VHB 4910 means 1 mm thickness. VHB 4905 0.5 mm thickness. VHB 4925 0.25 mm thickness. Now you see different tapes have the different advantage. VHB 4910 larger thickness, okay. It is having a larger thickness. You apply, for example, without a pre-stitching, you apply a particular voltage. You will get some actuation. Getting my point? So at a particular threshold voltage, it will get fail. We have seen that if we keep on continuously increasing, so thinning will take place continuously because opposite charge will going to attract each other. We have already seen that. So a stage will come at a threshold voltage, the electrical breakdown of the membrane will take place. That is called as pull-in instability. We are going to discuss that thing. So you can see the electrical breakdown will take place. And if you see for 1 mm thickness membrane, your required threshold voltage for the failure will be high in comparison to 4905 and 4925. You are getting my point? How? The reason is its initial thickness is high. When you apply the voltage, what we are doing? We are compressing in the thickness direction and we are expanding in the aerial direction. So larger voltage is required to get the electrical breakdown of the VHB 4910 membrane. Okay. So a experimental data is being available that we are going to share with you, no problem. Ki how the thickness will going to govern the threshold critical voltage. And the important thing is, for example, if you are pre-stretching the membrane, okay, that will also play a very, very important role. So that's why we are planning to show you the pre-stretching mechanism and the membrane with the different thickness. We are having only like right now 1 mm thickness membrane with us, okay. So what is the concerning effect? If you pre-stretch, what is happening? Pre-stretching, you are basically expanding in the aerial direction and reducing in the thickness direction. So now you apply the voltage. If you have a particular pre-stretch membrane and without pre-stretch membrane, unpre-stretch membrane. For unpre-stretch membrane, if you require a particular voltage, for example, for actuation of the membrane, less voltage is required in the pre-stretch membrane to get the same actuation. Why, you understand? Why? Is any reason? Already you are providing the initial, but basically the potential difference is creating. What it is going to do? It will ultimately going to provide an electrostatic force of attraction that will going to compress the membrane and that will be responsible for the deformation. So initially if you provide that thing, so you can say it is like an initial preliminary thing that you are providing. So that will basically support. So larger, there is one concern we have seen that in dielectric elastomer membrane, major concern is high voltage requirement. So one of the method is if you provide initial pre-stretch, so less voltage is required to get the same actuation as required for the unpre-stretch membrane. That is one thing, very, very important. That's why I say pre-stretch play a very, very important role in dielectric membrane. Okay. So Keshav, can you show them the VHB tape? So this is, I am telling you, this is one of the alternative of this VHB tape. This VHB tape, one bundle costs around, it's very costly, 10,000 rupees. A small bundle of 1 yard almost. So there is another tape that is being available.
In lab also we have.
In lab we are having VHB 3M also, we are having that. And this is the other tape having same property, it is around 800 to 900, same bundle. So for our students, like if you are rigorously carrying out the experiment, as an engineer we have to look into effective properties, like if you are getting the same result, almost the same result, so we can utilize this one. So what we are planning, we are also trying to get all the properties of this membrane, since 3M VHB 4910 is commercially available. All the properties we know. But this is another type of tape that will have almost the similar properties with very less cost, almost 110. Oh, almost you can say that one is 1,000 rupees, one is 10,000. So 1/10 is the cost. So it is giving almost the same actuation we have observed. Okay. So we are trying to find out all the other properties like electrical breakdown. Okay. So whether it will provide the same electrical breakdown as 3M VHB 4910 is given. Okay. Let's come to the second part. We are required to produce the active area, because at that active area we are going to apply the potential difference. Okay. So that is basically done with the help of a carbon conductive grease. Okay. That carbon conductive grease is basically we are using, and it is widely used. Not only we are using. So many of the researchers working in this domain, they are using MG chemical 846. Okay. So this is we are having with us.
3,500 cost.
So this is the carbon grease we are having. If you want to see, like we can show you also. So this carbon grease is basically, what is its function? It is used for making electrodes. But it is very viscous, I will tell you. So how we are doing to fabricate, like utilize it? So we will have some tarpaulin that will not affect its conductive property. We mix it with the help of a brush in a container. Okay. Then we are going to, after like some saturation, after proper mixing, then we have implementation for the active area. I hope you are getting my point. So it's not only one of the carbon grease that we can utilize. Other type of conductive grease are also available, I am telling you, but the carbon have very good conductive properties. That's why carbon conductive grease is widely used. So whenever you find the research work, like experimental work on dielectric glass stone, at most of the places, this carbon conductive grease is used. Okay. And it's also like, if you have this tube, it is cost around 3,500. Okay. So, but the thing is, this can be used for large number of experiments, because you are using a just small amount of paste and mixing it with the oil. Okay. And that you can, and it's not like that. For example, if you keep it at the room temperature for a long time, then again it will trying to go back to its viscous behavior. So it will become little bit thicky. Then again when you start keeping it use, if you want to use it again, just apply a tarpaulin oil again proper mixing is required until or unless it become at least up in a way that you can properly implement on the active area. You're getting my point. You can again reuse it. That is the one of the good characteristic of this conductive carbon grease. Fine. So this 846 is nothing. This is MG Chemical Company. So he has its like a chain of the component. So they are now at 846. Like Microsoft version, we are having different versions. Okay. So the third ingredient or the component is copper strip. Very important. So the copper strip is used. You can see here. This is a copper strip we are having. Okay. So this copper strip is basically used to provide the connection between that carbon grease that you are providing with the terminals. So for making a proper connection between the carbon grease that you have applied, the active area, to the terminals. Terminals means basically from where you are going to supply the voltage. So this is simple copper strip is used. It's very like conventionally we are available. You can easily find in the market on Amazon, on all the other apps. Okay. So you can get it. So what its property, when you put it and you just remove one of the layer, it will basically stick to that. Since our VHB tape is adhesive property, over that you have put the carbon grease, still it possesses the adhesive property will be there. When you put it, you need only to press it. And one more thing, for the proper connection, always on the copper strip in the active area, again paint that copper strip. If you paint it, there is a very chance of the leakage of the current from that location. So usually what you see, the failure will take place at the joint of that copper strip with the active area. At that particular location, the failure will take place. The reason is, First thing is, again, it's a intersection point, okay, and when you are supplying it, initially it will get generated, or it will reach to that particular that location, it will basically going to spread out. So that is more susceptible area. You're getting my point? So on that area which is in touch with the active part, always put some carbon grease over the copper strip, and that remaining you can directly connect to the terminal. I will show you also the complete picture of that, okay. Then that what I have discussed, the frame, your basic transparent file that you are using at your, basically in your lab basically. So you see that material is PET, polyethylene terephthalate frame, okay. So all the basically chemical composition, I have a notes I will share with you, I have bring here also. So you can go through the chemical composition of that, how basically they are manufactured chemically, okay. So you see there it is commercially available in different thickness, 0.1 to 1 mm thickness. Depending upon the application, which membrane you are using, which frame is suitable, okay. For example, if you want very large actuation, you can go for small thickness frame. Why? If I go for a small thickness of the frame, what will happen? It will resist less. For example, if you are making a DMS actuator, so we have seen that the larger the stiffness offered by the frame, less will be the initial configuration or the attained angle of the DMS actuator. So you can see, depending upon your application, where you want a minimal, like small amount of actuation but large stiffness of the entire structure, go for the frame with the higher thickness. And vice versa with the membrane. You can tune both of them, optimize, you can take the optimized parameter to get the optimized actuation range of the DMS actuator. Is it fine? Okay. So this is the, that one of you have asked, that stiffener. Basically stiffeners are made up of this polylactic acid material, okay. So this is basically, we are having also this, you see, there is a spool of that. So you continuously put in the 3D printing machine, okay. And in that 3D printing machine, this spool is it, you can continuously pull it, and it will, you can basically extrude it, and it is going to implement. So in the solid work, basically you have to design the component, okay. For example, if you want to develop some casting types of thing, you fabricate that in a basically in solid work you design it, provide a command in the 3D printing machine, and it will continuously going to extrude that and fabricate the component for you. So we are having that thing, I can show you.
Yeah, this is made of PLA.
So this is made up of PLA material. So what is this? We will show you also. It is ultimately the stretching mechanism. So we are going to attach some spring component to that. So you see, it is made up of PLA material. And you see the finishing is also very, very good. Okay. So depending upon your 3D printing machine, the quality it will have, so your finishing, surface finishing will also going to be increased. So this PLA material, if you are using in a normal 3D printing machine, it will provide a very good surface finish also. Okay. So this is one thing. That's what I am telling you. So the other component is CAD model. Initially we prepared a CAD model of the stretching mechanism. Pre-stretching is very, very important. We have already seen, I have already told you that pre-stretching is very much required in DMS actuator. Why? Because it will initially provide the strain energy of the membrane that is used for the initial bending of the structure, okay, and that is used in the gripper for holding an object. So when you apply the voltage, in the second case, again your strain energy will going to change and you will get the other motion, okay. But initially pre-stretch is very, very important. So this is the CAD model of the pre-stretch mechanism. We have already shown you the experimental one. This is the spring element that is made up of stainless steel. So you put it, arrange it in this mechanism that you have developed with the help of PLA material, okay. And after the assembling with the help of the screws, you can arrange it. So this is the spring that we are talking about, okay. So we will show you everything in person. You can come here, and after that, after session you can see. So this is the stretching mechanism. You can do it uniaxial stretching, okay. And if you avoid like biaxial, you can also do this. So you can see the initial dimension, it can go up to a very large pre-stretch. This is around 8 by 8, I think, okay. So that you can basically pre-stretch up to 4 or 5 times. So that is very much required, pre-stretching. Simple mechanism we have utilized. Initially I will tell you, this is the stretching mechanism. Earlier how we have done pre-stretching, when we have started our research work, so we have a chart paper, we made a square block at the center of it, okay. We have this spring with us. So we put that spring and put it 4 thread at the corner, okay. So manually we are stretching it, and when we get the stretch of the membrane, we put the membrane over that and stretch it. When you put the membrane, it will provide a lot of force in basically the stretching, okay. So when you put it the thread, earlier there is a chance that some manual error will come, so sometime it will come back little bit, because you are providing a larger pre-stretch, then the membrane is offering a resistance, and with the help of thread, if you wind at the corners, so we have seen that some, for example, we are giving pre-stretch of 4 or 5, it's very, very difficult to give. Then as advanced stage, we have put it in this, like we have developed this CAD model and 3D, and again we have done a further automation. I will show you. We have, initially it's manual, then semi-automatic. Semi-automatic, I am telling you this because we are having some control that at least it will provide an initial holding of that on object. Then we are pre-stretching with the help of this, basically this mechanism that we have developed. We are not pushing that spring. Now in the fully automatic, we have done all the electronics control of that. We just give a command, it will automatically take. We have that also, we will show. Okay, so step by step we move forward in this regard. Initially with the manual fabrication or manual stretching, then semi-automatic stretching, then fully automatic. So our life become very easy. So fully automatic, everybody nowadays, we are a lazy people. So what we want the easiest method. Yeah, you have any question?
You said that that stretching will actually try to make that whatever that iron block is there, that is stretching mechanism. It will try to push it inwards because of resistance.
That stretching mechanism will not offer resistance. The membrane will offer resistance. When you put
membrane will offer resistance to make this.
To try to come back, to make it come.
But this PLA material, is it strong enough to resist that?
Yes.
If you are only using this PLA, is it stronger than that frame that it can resist that much force? Like 1 mm thickness frame is very resisting. Higher thickness it will be more resisting. So is it that enough, like for 4 times, 5 times stretching, is it enough strength in this to hold that?
Very good question. So I will tell you, just show me. This is the small one. Very nice question. So it will not go to a very high pre-stretch. This is the small structure we have developed. It could go to maximum 2 pre-stretch. And how it is happening? We are having basically, you see, it's when we stretch it, we hold it like this, and we have a screw mechanism. It will hold at that location. So that will also help in holding that thing. First thing is that. For the larger pre-stretching, 4 or 5, that's what I have discussed here, you require to make it more like a stiffer component of the PLA material with the help of it. So we will make a more larger component of this. Along with that, we are having a screw mechanism to hold that at that location. You are getting my point? So your question is very much right. If we are using for the larger pre-stretch, it's very difficult to hold that. So you have to design this thing. So when we are designing in the CAD modeling, we have to look that if we are providing a very large force to that, whether it is holding that object or not. So that is the required thing. So his question is right. If we are we are going for the larger pre-stretch, so we have to design this stretching mechanism. Stretching mechanism is, it's a combination of this spring and this in an optimized way. So the other way we will show, the larger one we will have, you can see. 1 second.
Means this is majorly for the accuracy of the stretch.
Yes. So what it is happening, earlier, that's what I am telling you, when we provide manually. So what is happening, you are trying to push, VHB membrane is being stretched straight. So it is basically spring, when it go to a particular, it will not try to come back. You can see, you can show that spring only. This, for example, if you stretch it, it will not try to come back. It gets fixed. But the membrane which is being stretched, it will try to resist it. So it will try to make it come back. So you are getting my point. So that membrane basically is trying to come back. So when we are doing manually, definitely we will, how much we are trying to make it with the help of thread to get faster at that location. But sometime it will come little bit. So yeah.
So stretching is done by actually simultaneously, or first you actually in one direction then other?
Initially it can be done in both the direction if you are having a 2 operator. Manually what we have started, you see, in this mechanism you can do in both the direction with the help of 2 persons. So it's like that I am stretching from here and the other person we all at the same time can stretching from here.
Both have to be done at the
Both have to, there are two ways. If you are pre-stretching like uniaxially if you give and then in the other direction it will not give a proper biaxial deform.
That's what I thought.
It have to be in parallel.
It will change the properties.
When we are doing manually, we are basically two operator we are using at the same time. He is pushing in one direction, I am pushing in another direction. That's what I am telling you. Some manual error will creep in at that time. In this one, basically, we will show you. It will take a one go. In one go, it will have a biaxial. It depending upon the command you give, uniaxially you want or biaxially, it will go parallelly. That's what the role of fully automation will come into picture. Getting my point? So before going into that, we are since dealing with the stretching mechanism. So can we show this stretching mechanism? So this is very, very simple. For square, like we are having a simple membrane, it's very easy to basically get the stretching. But if we are basically working on the radial stretching mechanism. So you see that radial stretching play a very, very important role. Yesterday, Professor Prashant Saxena shows a radial, because of the radial stretching, after the application of the word, wrinkles will be developed. So radial pre-stretching is required when you are putting or developing some circular type of membrane. In that case, it is very difficult to stretch radially. So for that radial stretching, we have developed the fully automatic stretching mechanism we are having here. So if you want, you all can come here. That will be very good. Visualization is very nice. So online participant, I can share the video with you. Right now we are showing to the in-person candidate the actual radial stretching mechanism. It is fully automatic, complete controlled electronics. So we are just giving a command and we will have the radial stretching in the required radial stretching in required dimension. Okay. ये ऑनलाइन दिखा सकते हैं किस तरह से शेयर अंकुश trying to bring it at the center so that online participant can also see the developed fully automatic stretching mechanism. We have already filed the patent for that also. Extension है वहाँ पे? The fully automatic radial stretching mechanism developed here. Okay. One thing you can do, one of you can join from the mobile and just share your screen and point it at this place. You getting my point? So that is quite easy. कहीं भी लगा लो, we are going to share with the help of a mobile. We can do that. So online participant, is the mechanism visible to you all?
Yes, sir.
Okay.
So before going through
Just
this,
one. So what we will do, initially we will have some option of fixing that with the help of the screws. Just you
go
see.
to the instruction that it will operate on the 12 volt and above the range of this voltage. Okay. And first of all, we have two options. First is we can go through the stretch ratio, suppose 1 to 1.5, 2, and other in the mm also, 30 mm, 40, 45, 60. So this is the knob, okay, and I will just initial radius, this is the membrane attached here, and the radius of the membrane is 30 mm, and we want to suppose go in the stretch value of 2, final length, final radius, and to the initial radius is, then the ratio will be 60 by 30 is 2. So and if we stretch, then go, it is expanding to the stretch value of 2.
So there are two ways basically.
Yeah.
Initial radius 30, you
Yeah.
put the value at 60. So 30 mm to 60 mm means your pre-stretch will be 2. Other way is directly you have a stretch ratio, you put 2. So after initialization, in the initialization you will get two options, either dimension wise or stretch ratios.
Yeah. And suppose in the expand value, suppose we are initially we have the lambda is equal to 2. Now we have to go to 3. Then it will continuously go by this way.
From 2 it will not come back, it will go from 3.
3 also. And this is auto lock. The mechanism will stop here.
So if you see, we have used the gear mechanism for the development.
Yeah.
So what type of gear is this? Have you studied this?
Yes.
पर गया इस पर
For
नहीं
Bomb
बॉम्ब
gear है?
बॉम्ब
Gear. Okay.
And then this complete structure made of with the PLA material, the gear, and we have developed in our lab also, lab through the 3D printer.
So you see this entire part, this base, this one,
acrylic material
acrylic
sheet
material
is
sheet is there,
cut
and
by
this is
the
entire
laser.
part is made up of PLA.
Yeah. And this is the Arduino arrangement. We have just inserted here below side, and this is the motor we have used. This is the specification of motor.
So I hope this will be of interest to you. This is a radial stretching mechanism. Similar way we can have, that will be very simple for the square mechanism. So you see now it's fully automatic. We just have to give a command and we can get the final output. Is it fine? You all can come in. एक picture ले लो. So that's what I am discussing. Like we have initially started with the manual. Okay, manual stretching mechanism. Take it to the semi-automatic and then fully automatic. So that's why we are basically evolved also. In our life basically we also evolved like this. This is the actual way of fabricating the simplistic rectangular bending actuator. So you can see step by step. We have already seen this stretching mechanism. Okay. Then what we have done, we have stretched that mechanism. Okay. And in that pre-stretch mechanism, we have all this ingredient ready with us. Frame, stiffeners, carbon grease with us. We one by one we are going to put it that. Okay. Then with the help of a razor blade, we cut that component. So initially in the assembled view, it will look like this. Okay. When you cut it, basically this is the basic experimental mechanism that we have followed. Schematic of the experimental mechanism is being shown here. So after this final stage, we cut it with the help of a razor blade. So what will happen? It is a pre-stretch membrane. And if you see, there is another stiffening frame we have provided at this location. Why? There is a reason, not at this, at the bottom side of this, so that it will not allow to get it bent at this location. So we want this bending will start, it will be basically it's like this. Okay. So that's way the tuning is depending upon us, that how we are going, which shape we want to get. So based on that we will select the shape of the frame. Additional stiffening element like stiffener we have provided. So this stiffening frame is nothing, it is the same component frame, one more layer we have attached. You are getting my point? It's not that something stiffening element we have, the very element of like PLA material. It's the same PET material we have attached, we have cut a square cross section for that and put it over that. Okay, just to provide a stiffening response there. Okay. So the actual one, now you can see, this is all we have shown here is the schematic representation. Now experimentally you see it look like this. So as an engineer we have to utilize this tape in an effective manner. So for a one particular pre-stretching, we can put different DMS at the same location. Different DMS means the spacing. You see the spacing is 1 centimeter, here the spacing is 0.75, 0.5, 0.25. Okay. So in a single go, so it's not like that for a particular one spacing you develop full stretching of the membrane and that put 1 centimeter. No. If you want to analyze the effect of different spacing, just put it in a single go. And there is some partition tape we have provided. There is a reason of providing partition tape, so that when we cut it, that partition tape will basically help in removing individual component of that. Otherwise, if we cut one, the entire tape will be trying to come back. So that's the importance of putting the partition tape also there. So you see, you will face a problem and you will basically develop an idea to overcome that. So after cutting all this, this is basically the experimental setup. It's not of IIT Indore, I am telling you. We have done at IIT Roorkee and Germany I have done. So it's of IIT Roorkee setup. I hope a lot of labs, like we are still in the upcoming 2 or 3 weeks, we have all this equipment with us. We will have the setup, soon it will get ready. Okay. So it's like initially we are having a vibration isolation table. That's very, very important. You are supplying a very high voltage. Oh, it is very much required. Okay. So it will be basically used for the vibration isolation is used for what? Damping the vibration. Okay. That is one thing. Then we are having a high voltage amplifier. So In India, what is the voltage supply we are having? 220 volt. So now you need to basically amplify that because you require the voltage of kilovolt. So for that we are using high voltage amplifier. In that high voltage amplifier there is basically we are having an option like nowadays it is basically integrated with the supply voltage level, like if you want sinusoidal voltage supply. Okay, AC voltage I am talking about. So what you can do, you can have the option of that. Sinusoidal waveform, square waveform, rectangle, whatever you want. You can decide that thing also. So this is the basic experimental setup that is going to, you have, if you want to develop a lab, you have to utilize this basic experimental setup. Okay. Now that I am discussing, initially we started with the development of the DMS actuator without stiffener. So what type of structure we are getting? It's a very first crude experiment that we have carried out, and this is the result we have obtained. So it's a very initial experiment. Then what we have done, we put the stiffener. So there is one disadvantage the stiffener will have. Have you observed that? It's not, every coin has two aspects. You are putting stiffener, we are getting a lot of advantage, but there is one disadvantage is also that. What is that? Actuation will reduce. For example, if you are not putting stiffener, it will bend like this. But because of the putting of the stiffener, because of the mass of that stiffener will come into picture, it will not allow it to get bent more. You are getting my point? It will provide lot of advantageous effect, warping avoiding, governing the attained initial configuration, actuation range by providing twisting and bending modes, but there is a disadvantage also, or limitation is that it is initially going to affect your attained initial angle. So what are the different methods? Can we have any other option instead of putting stiffener, but we want stiffening response in the membrane? So anything you can think as an engineer? Yeah, please tell. We put anisotropy. Yes. So during fabrication or the fabrication of the dielectric membrane, there is some, you can see initially in the membrane material, if you can put some anisotropic behavior along the required direction. So no need to put all these stiffeners and all this thing. You're getting my point? So that will be basically a part of material engineer, that how when we are basically fabricating that, manufacturing that material for a particular application. So it's not like that always is going to put the initial fiber in that. For specific application, for example, we want to use them for the DMS actuator in gripping application, then we say that we have to put initial fibers in required direction so that the implementation of stiffener can be, we cannot going to use the implementation of the stiffener. Okay. So the experimental that we have shown here, when we have cut it with the help of a razor blade, so it will give you a obtained equilibrium configuration of the DMS actuator, initial configuration or equilibrium like this. So you see, when we have keep on increasing the spacing between the consecutive stiffener, our attained initial angle that we measure from the horizontal keep on increasing. So this green color board I have already discussed with you. What we have done, we have basically the stiffener. So this is basically at this location we are having the cross section of the stiffener, outside region of this DMS. It is not at the outside, it is at the periphery actually. So at that particular location, we simply cut a green, very thin, you can say a paper of green color, and we put it at that cross section. So I've already told you there is an advantage that image processing technique. So what we can do, if you measure this angle manually, you can also do, but to get an exact angle. Okay, when we are doing manually, that is definitely a chance that you measure 1 or 2 degree difference will come. Okay, so for that, what we have done, we have developed an image processing technique, very, very simple code I will share with you. So what it will done, basically, it will take as it is an input image. Yeah, I can show you step by step. So as an input image, we are having this, okay, this initial shape, okay. Then in the MATLAB code, we have defined it like that. It will be taking it as a green channel. So it will decide it, what it will do, it will make only the green part will be get highlighted. Green channel image we have made. So it will be the green part, this one So it will be focusing on that. Then we say the grayscale image. So except the green part, green is being highlighted here, the other part will become grayscale. So when you subtract the green channel image from the grayscale image, what you will get? Only this remaining part. Only the part that is having the green part highlighted. So you will get this. So we have just zoom it. You can see 1 here, 2 and 3 like this. So it's not maybe that much clearly visible, but you can see this cross-sectional view come here. Then it is basically a subtracted image. Then in the MATLAB we have converted into a binary image. 0, 1 like this. Binary image it will be converted. So it will be showing it can easily get visualized. So this is, you can see the cross-section of this stiffener is being here. Then what we have to do, we say that whatever the view we are getting, just put the center and contour of that. So after putting the centroid of this cross-sectional area and the centroid of that, we have then joined with the help of the lines, horizontal and vertical lines. So we are having theta 1 and theta 2. So for example, if it is from the horizontal, it is lifted little bit. So that the difference, initially your angle will be like theta 1 minus theta 2. That actually it should be directly theta, but what is happening if you see here, if you go back, it is little bit lifted from the horizontal also. So that will be taken by theta 2. This is theta 2, very small angle that is being lifted. So when you subtract that theta 1 minus theta 2, you will get the theta value. That is the actual angle of the DMS from the horizon. So that's what I'm telling you, that theta 2 we are going to miss when we measure manually. Okay. So that's an image processing technique. I will share the code with you all. So you can practice, like just an input image required. Similarly, this is an input image for the equilibrium configuration. For the actuated configuration, you will have different image. So just put it here that input image will be the actuated image. So you will get one angle for the initial bending and one angle for the actuation angle. So you take the difference, you will get the, what you will get? Actuation range or actuation stroke. Fine? Okay. So this is the experimental fabrication, you can see. We are getting a very good actuation, you can see. It's not like that it's having a very less actuation. That actuation also keep on increasing, or we can tune that depending upon the voltage supply, the frequency that we have discussed. So it can basically, we can control that thing. Is it fine? I have also shown you yesterday a lot of videos that is basically give you a glimpse that how the change in the applied voltage or the frequency will affect the actuation of the DMS actuator. Okay. So any question till now? Divyansh, you have any question? Now the concern is that I have told you, simplistic case we have started. And that's what the research is going like this. So people are doing what? They have developed a simple bending actuator, then club them together. Okay. So this research, if you find the paper, what they have done, they have developed these 3 types of bending actuator. They club them together, you see, and develop a flapping wing. In another research, they have developed different fingers, or you can see a large type of bending actuator. Then they club together and produce a gripper. Here they produce a flapping wing, here they produce the gripper. Again you see, this they have individually fabricated, then clubbed them together. For frog type of actuator, they develop this and then assemble on a common body. Now, there is a huge disadvantage they have also observed. Initially during the research, they have pointed out that they individually fabricate them and club them together to develop some structure, final configuration. But initially after the development, the problem is that the failure will be taking place at the assembling point. That is quite anticipated. Okay. But in the initial state of the research, they can do like this. They say, we have developed this individually, they are working very well. We have an option of clubbing them together to obtain the assembled configuration. That will initially also work, but it will be, durability is not that much high. So you are getting my point, durability will not be there. Definitely it will be have a failure, and that will be at this intersection point. So to overcome that issue during my postdoc, that I have developed an idea why we are considering the different frame and then clubbing them together with the help of this DMS configuration. We can have a single compliant frame that have the desired shape of the final configuration. It's a simple idea. You can also think ki if we not need to assemble anything, then the durability or the chance of the failure will get reduced. The problem is you have to fabricate in a very effective manner. That is one concern. So what we have taken a shape of the compliant frame in such a way that when it will get assembled with the D membrane, so the output or the final configuration we want, we can govern with the help of the initial configuration of the frame. I want to develop, for example, a gripper. So I cut 4 fingers in a single go in a complete frame, and then I will paste that frame over the pre-stitch membrane. So you can see stiffening is being here at the center. When the pre-stitching is being there, all the legs will try to bend. So that is one thing. Flapping wing, why we have to assemble different configurations? Just define the initial set of the frame in such a way that the output of your final configuration will be governed by it. So we define the flapping wing, and that's why I have told you it's not like that. Random nahi hai. It's not a random we have selected. So we have basically taken all the shape from the nature, motivated from the nature. So we have also put the stiffeners. If you see the starfish, and you can see complete resemblance. Okay. So initially we have also started not like this. We have this diverging length, rectangular cross section of the gripper. They all are giving the results, but to get an optimized shape which will give you a best actuation, best gripping effect, we have to go through some research, and we find that when we are considering the shape of a natural organism. So as a God, if you see, the God is the best engineer. God is the best engineer. Whatever we will develop, it's less than that what God has created. So you can see the movement of the starfish, of octopus arm. We are trying to replicate that thing, but still we are biomimicking the response. We are not able to produce the exact one, but we can take the reference. So when we take the reference, you can see the starfish actual configuration is this, and we are trying to get the exact shape, not the exact, but the biomimic the shape of the starfish. Similarly, if you look at the actual dragonfly, it will look like this. So if you just open its flap like this, so it will not exactly like this. The reason is, if you see, there is some stiffening response or fibers will be there. I am talking as an engineer perspective, it's like a fiber. It's not that fiber. So we are trying to put stiffener on the flapping wing if we put it at a certain orientation. But that is also a crude approach. The right approach, as he has pointed out, during the fabrication of the D membrane, if we can put something like this, then we are going to exactly replicate the motion of the dragonfly. But as an initial attempt, what we have done, we have put the stiffeners and at a certain orientation. So we will have the replication, or we are trying to replicate the motion of the dragonfly. Okay. So again, the stretching mechanism, all the approach will be the same as that of the bending actuator. So what is this? We are having now the frame that will have the shape of the gripper itself. So we put it step by step as we have done in the bending actuator. We put it all this case. Okay. So this is the actual stretching mechanism we are working upon with the forearm gripper. So when we release it, so this is the initial attempt I am telling you. During my postdoc I have done that. This is an initial attempt. So what is happening, if you see here, different copper strip is required at the different junction. Okay. So what is happening, the bending of the all legs are same. That is one thing, the good thing that we have observed. But we have considered initial pre-stitch of 2 in both the direction. So it will bend the legs more, because the more strain energy is being provided by the membrane to the legs. So this is an initial attempt we have done with the pre-stitch of 2, because we are anticipating if we take larger pre-stitch of around 2, good pre-stitch of 2, we will get good actuation. So what is happening, the leg will curl, because we are providing a biaxial pre-stitch of 2. So it will be very high pre-stitch. So then we evolve we take less pre-stretch or uniaxial pre-stretch, we keep on evolving with that and we find a very good gripping of that gripper. Okay, all that image I will share, but to basic understanding you can get it from here. You see, this is the actual experimental forearm gripper that we have fabricated. Okay, then this flapping wing that we have discussed. So this is the 3D PLA reinforcement I have already discussed with you. Now this is the stretching mechanism that you have the view here. Okay, and when we release it, it will look like this. So this is the initial configuration, no voltage is applied. Okay, in the second stage, we have already have the copper sheet, we have already have the carbon grease. You see, we have already connected with the terminals to that also. In the second stage, when we apply the voltage, it will actuate. I can show you all the thing. So this is an deformed DMS initial configuration or equilibrium configuration. In the second stage, when the voltage is applied, it is called as final or actuated DMS configuration. Fine. So I have already shown you this thing, but experimentally how we move ahead, then we replicate the motion of a dragonfly. Okay, so this is an idealization and this is the experimental model of the DMS, based prototype of the dragonfly. So any question till now? So you are getting understanding. Start with the bending actuator, take it to the advanced stage. We have developed the forearm gripper, flapping wing, dragonfly. Still we are in the future planning to develop the motion of a butterfly also. So the motion detection or the actuation is not the requirement. It's very, ultimately whatever you decide or define, ultimately it will give you an actuation. Why? Because dielectric elastomer is responsible for that. The thing is how you are going to take it in the future application. So you see there is a lot of advancement is required in this. So we have already write a project in the advanced research grant that we are basically going to develop the soft arm gripper actuator for space application, in which it will be used for holding some objects, and basically not holding, also for along with the gripping, it can take an object from one location to the other. That is very much required. Okay, so that is the second stage. Initially you have to develop, you define that your model is working well, it is actuated. Now advancement is required. You need to have a controlled operation of that. You have to put some sensor, you have to integrate with some sensor and actuator controlation. You say that at a particular point it is going to exert a force, one of this like arm will going to bend and it will hold an object. Then with the help of the sensor you say that it is going to, after gripping that an object, is going to place it at a different location. So that is the second stage. Okay, so this is the initial stage. We have already developed a lot of things. Okay, now listen. So the first technique, I hope you all understand, experimental correctness, very, very important. So that is one thing we have already discussed in detail. If you have any doubt, you can come later on also to discuss, or still you can ask. Now the important part is analytical modeling. I have already discussed you with in detail how we have done the analytical modeling. Now I will show you how you can solve these equations, okay, the complex equation that we have developed by using the MATLAB. So that will be a very good practice exercise. If you have your laptop, you can open, otherwise you can follow from here. 1 second, Ankush, don't share screen. I will just. First I will give a glimpse of the paper that we are going to show you. अभी स्क्रीन शेयर कर दिया क्या? 2 मिनट बैठो, ठीक है. So online participant, is my screen visible?
Yes, sir.
Okay. Are you able to see the paper that I am sharing?
No, sir. Just see the online MATLAB screen.
Okay. अंकुश मुझे शेयर करने दो एक बार. अभी शेयर बंद कर दो आप. Now is it visible?
Yes, sir. The paper is visual now.
Okay. So the second case that I have discussed with you, that incorporating anisotropy plays a very, very important role in DMS. So when you put in the DMS actuator the fibers in one particular direction, so what it will be helping? For example, if you increase the strength of the reinforcement, so your attained angle, initial angle and your final actuation angle is going to vary. So just a quick showing of that thing, how we have done, and I will show you how with the help of the MATLAB we can do this, solve this analytical model, okay, numerically. Okay. So we have a very, I will show you like step by, not going step by step, that's a crude overview that how we have basically developed the final model. Okay. Initially, we are having this our DMS actuator. Okay. So it consists of a fibers in direction 1. So we have basically considering a case of transversely isotropic. Transversely isotropic means in the transverse direction the isotropies will be there. So only the fiber is in x1 direction, in the other direction the property remains the same. Okay. So what is happening if you have this schematic view, side view also, you can see that this is the side view. The theta is the angle that the frame has made with the horizontal, or the entire configuration is made with the horizontal. So it is called as initial angle when no voltage is applied, and it is called as bending angle or final actuated angle when voltage is applied. Okay. Membrane has 3 configuration: initial but with the fiber, pre-stage configuration and actuated configuration when voltage is applied. 3 configuration are there. Okay. So that is the importance of what Dr. Prashant Saxena is discussing. Deformation gradient, okay, Lagrangian description. So that is nothing. You are basically describing the stretch in direction 1, 2 and 3. It is final dimension upon initial dimension. Okay. Then you can define the deformation gradient. Okay. The deformation gradient of the membrane is, if you see this expression we have considered, the length of the membrane is 2c by theta sine theta by 2. This is not like a random value we have taken, the random expression. It's not like that. It is satisfying the initial condition. When theta is 0, in this case when theta is 0, your L is equal to C. You can basically check that thing also. L hospital rule you apply, you will get that thing. So it means that this expression is correct. Now lambda 1 is basically the stretch in this direction. So it is final length upon initial length. So initially if you go, that I have shown you in the PPT, that it is L equal to C. Initial length that I have shown you, the simple rectangular frame that we have considered. So by putting that expression, we get the value of lambda 1 to be 2 lambda p by theta sine theta by 2. Lambda 2 is 1, lambda 3 is incompressibility. Lambda 1, lambda 2, lambda 3 is 1. Since lambda 1 is lambda, lambda 2 is 1, so lambda 3 is 1 by lambda. Okay. Now the deformation gradient, the principle of the diagonal element, the principal diagonal element, lambda 1, lambda 2, 1 by lambda 1, lambda 2. What is that? It is lambda 1 and 1 by lambda. Fine. Now the important concept comes. So whenever you are incorporating viscoelastic behavior or anisotropic behavior with the viscoelastic one, you have to consider certain rheological model. We have considered for viscoelasticity which model? I have shown you yesterday, Jenner model, Jenner rheological model. So that consists of a Maxwell element connected in parallel with the spring. I have also tell you why I have considered Jenner model. There is a specific reason. We can consider simple Maxwell or both phenomena it can take into account effectively. It is the simplest model that take stress relaxation and the creep at the same time into picture. Getting my point? So now we have incorporated anisotropy also. That anisotropy along with the viscoelasticity. definitely we are going to have a matrix and the fiber. So in this case, we are using the same Zener rheological model, one for the matrix and one for the fiber. So now the rheological model is the Zener one, but it is having the two components. It is having one for the fiber and one for the matrix here. Fine. Now the concern is your deformation gradient. Actually, you have to decompose into a multiplicative decomposition of it. So now why multiplicative decomposition? Is any reason you can tell? Like F is now decomposing into two parts, elastic and viscous, Fs, Fv. Why multiplicative? We can have additional also, we can have subtraction. Why we have done multiplicative decomposition? Anything you can think about it? We are incorporating anisovisco effect, okay, viscoelastic effect, okay. So anisotropy we are taking with the help of a D, fiber and matrix rheological model. What we are doing? The deformation gradient. We are decomposing multiplicatively into Fs and Fv. Fs is for the elastic part and Fv is for the viscous part. Multiplicative क्यों कर रहे हैं?
पैरेलल में कंसीडर किया है दोनों से,
Okay.
तो इलास्टिक पार्ट और दोनों विस्कस अगर सीरीज में होते तो ये होते शायद।
अगर आप सिंपल एक मैक्सवेल मॉडल ले रहे हैं in which spring and dashboard is in the series, then you again have to do the multiplicative decomposition. There is a specific reason behind it. If you see, lambda viscous is the internal variable that you have to evaluate. Viscoelastic will come into picture. Whenever it comes into picture, there is an internal variable, lambda viscous, the stretch that is developed due to viscous effect. You have to find out that thing. And it is being observed experimentally that it is going to be the value, it will attain a value lambda into lambda inverse. You are getting my point? If you are directly find out lambda viscous to be lambda minus lambda inverse, experimentally it is observed that it will not give a right result. So when you decompose it multiplicatively, it can capture the actual effect of the lambda viscous, that is the internal variable. Okay, lambda viscous is an internal variable. So if you see here, F is what? F is this lambda 1 by lambda, or in the other case it will be different. So if you need to find out the value of Fv, it will be F into Fs inverse. Okay, so here lambda V1 is what? Lambda 1 into lambda S1 inverse. So lambda is lambda S into lambda viscous. So what is lambda viscous? It is lambda into lambda S inverse. So if you know the overall deformation gradient, take an inverse of the elastic element, then you find out the viscous effect of the lambda viscous, you will get an exact result. Or the variation that you will get along with the time will give you an accurate result. Okay, so that I will share that why we have taken multiplicative. You get the basic understanding. So simple way, if you want to evaluate lambda viscous here, it will be lambda I into lambda viscous inverse. Sorry, the principal says lambda SI they have written. Why? Otherwise you can write also lambda viscous as lambda into lambda S inverse. Okay, that is one thing. Now we have started with a very simplistic model. Which one is the simple model in hyperelasticity? Neo-Hawkian. So different models are available. Neo-Hawkian, Mooney-Rivlin, Gantt model, augmented Gantt model, Ogden model, Fung model, lot of models are there. But we have seen that all the models have their advantage and disadvantage. Neo-Hawkian one is the simplest model, okay. That will be very good and effective up to small, if you are not considering for the large deformation. So 2.53, it will give a very good result. But if you go for the higher stretching level, you see that it will keep on diverging from the exact result, experimental one. Okay, so we have started with the Neo-Hawkian model. That is one reason. For the simple calculation, ease of calculation, we have taken this. And so by putting the strain energy, like membrane energy, we are talking about the membrane energy, it will be by Neo-Hawkian isotropic equilibrium. Similarly, since we are considering the viscous effect, we will have the isotropic viscous, and there is another part will come into picture, anisotropic. So where this has been come, you see there is already person who have developed a polygonal model of transversely isotropic. Okay, so he has a complete derivation in which what he has done, he has considered a fiber in one particular direction, and he has developed a model through which he has given the strain energy of the anisotropic D membrane. So we have directly taken from them. So it's not like that what our forefather has done, we have to again repeat it. कोई जरूरत नहीं, you can take a reference directly. Okay, but take it from a good reference paper. It is not like that motion of actuator. So already, like Professor Prashant Saxena is working on this. We have already seen that always there are two approaches. If the problem is very, very complicated, start with the weak formulation, then land up to the final governing equation. You will derive, you have to derive. But if you have a simple like configuration, just use the Euler-Lagrange equation of the motion to get the governing equation of the motion. Okay, that is the approach. So here we already have all the simple configuration in which we have already defined our potential energy and the kinetic energy. So kinetic energy is very, very simple. It is half by omega square. There is one assumption I have already told you. Mass of the membrane is negligible in comparison to the mass of the flame we have considered. So that is one assumption. Now simple Euler-Lagrange equation of the motion we have implemented. So by putting the Lagrangian to be the difference of kinetic and potential energy, we get this equation. This is total potential energy. This is total kinetic energy. Lagrangian is T minus U, and after putting this expression in this equation, D is the Rayleigh dissipation function. Okay, that is being taken into account to develop an evolution equation. Evolution equation is required. Why? Because our lambda viscous evolve with the time. What is the like viscous stretch will be there, and definitely viscous stretch means it is going to evolve with the time. So for finding out, we require a Rayleigh dissipation function. With the help of that, we find the evolution equation. So evolution equation again come from the Euler-Lagrange equation of the motion, but the variable here is theta. In that case, variable is lambda viscous. Getting my point? So by solving this, you will get first this very, very complicated equation of the motion of the non-linear governing dynamic equation of the motion of this DMS actuator, that will have the term viscous effect, that is lambda viscous, and proportionality constant is here, lambda viscous, internal variable is there, that will have anisotropy parameter xi, okay, that will have an electrical effect, that is E term, okay. Why it is coming? Because we are considering membrane to be visco-anisotropic membrane, and lambda p is also there, pre-stretch. We have initially provided the pre-stretch also. So this is aniso-visco-hyperelastic membrane, we can see. So it will going to vary the case. If you put the like anisotropy parameter to be 0, what it will become? But the membrane will become when anisotropy parameter is 0. Isotropic. Okay. When you are considering anisotropic parameter into picture, it will be aniso-visco-hyperelastic. When you consider viscous component to be vanished, it will be anisotropic membrane only. Okay. That is like this. So you can play with the parameter. So you develop a generalized model. Now you say I want to solve for the isotropic, anisotropic part will vanish. Okay. So this is after incorporating some dimensionless terms, dimensionless parameter we have incorporated, and it will be basically coupled with each other. So frame bending stiffness is a function of mu something. So that is one reason we have done normalization. Okay. For the simplification, for one set of parameter you can have the different material property club in a same. Now this is the evolution equation for lambda viscous. Now we are having a three case. Initial condition is what? When the frame is attached to the membrane, initially structure is flat. So theta is 0. When theta is 0, d theta by dt is also 0. And we assume that lambda viscous that I am talking about, initially it will have the value of pre-stretch of the membrane. Definitely we require some initial condition to begin with. So we have taken that value, lambda viscous is equal to lambda p. It's not like that we have taken. It's already being observed that initial stretch that is being there, whatever the pre-stretch that you are providing. So the viscous stretch that is being developed in the membrane, that evolve with the time, definitely it will be there, but is nearly equivalent to the pre-stretch that you are providing. So some of the people you see, they directly take lambda viscous to be 1. But it's not right. It should be nearly equivalent to, for example, if you are providing a pre-stretch of 2, then you are taking 1, it will not give you the exact result. Some error will be. So it should be nearly equivalent, or you can directly take equal to lambda p. Okay? That is the basic understanding you have. The formulation, we will have a governing equation, initial condition, and the evolution equation. So I will now try to show you in the MATLAB there is a OD45 solver. Okay, I've already told you what is 45. RK method of fourth order. Okay, with a truncation error of dt to the power 5. What is dt? dt is a time step. So I will not go into very detail of the RK method. You already know initial condition you supply, you evaluate the next y like this. You have na y1 plus h0 by 2. You have already seen this thing. You have y equal to y1 plus h by 2 something, y2 plus y3 plus y4. So RK method of fourth order you have to go like this. But it is used to solve the ordinary differential equation. Okay. So that basically we have implemented in MATLAB. Now I will show you the basic glimpse that how we have to work with the MATLAB to solve this complicated equation. So one equation is this one, the big one. d square theta by dt square plus this big equation. One thing is this evolution equation and the other thing is initial condition. Okay. So I will stop my share screen. Now Ankush, you can share. On the other page, parallelly, we open that paper also. Is the screen visible?
Yes, sir.
Okay. So we are just,
Internal Explorer is shown.
okay. So the paper, the formulation that we have discussed, we will now try to show you that how basically you can solve this equation to get the important result pertaining to the dynamic analysis of the DMS actuator. Final equation and then MATLAB. Just go down, first equation. Okay. So here's the MATLAB code. I think it's visible to you. So the solution of a differential equation, we will go one by one. Initially we will have the attained equilibrium angle. So no voltage is applied. Okay. So if you no voltage is applied, can you show the paper Ankush? Just go back and go down. Final expression. Yes, this equation. So in this equation, your E square will become G. That's simple, quite anticipated. So how basically the angle is being attained? Because of the pre-stitch of the angle. You see, initial structure is that no voltage is applied, but we release it, so it will try to attain the shape like this. Why? Because of the pre-stitching of the mechanism or the pre-stitching of the membrane. It will basically try to bend the structure in a configuration. Okay. So this you see, initially we are having expression d2 theta by dt square plus kbb theta. Kbb here, remember, it is the frame bending stiffness. Lambda p here is the pre-stitch of the membrane that it's an initial, you have to define. So for example, if you want to pre-stitch membrane to 2 to 3, it's up to you initially. These are the parameters that you have to define. Kbb you say, frame bending stiffness, it is the ratio of, basically if you go a little bit up, it is the ratio of the different parameter by mu, T naught, L naught, W naught. So you say I will give a initial value to the frame bending stiffness, to the pre-stitch of the membrane, I will define all these things. Okay. What are the other parameter? Beta. So beta is a proportionality constant. What it signifies? Your spring has some shear modulus, okay, and you are connecting that Maxwell element with the other spring. So you say that the other spring, initially your top spring will have some shear modulus, okay. Now in the Maxwell element there is another spring is there. So the proportionality constant means your Maxwell element ultimately going to incorporate viscosity. So you are saying that the proportionality constant means how differ is your shear modulus with the spring shear modulus. So usually it is observed that it is 2 times. So the shear modulus, for example, the upper spring have a 30 kPa. So usually the spring in the Maxwell element will have 1.5 or 2 times the shear modulus of this. So we have considered the value initially like 2. So beta is a proportionality constant. That value you can keep it as a fixed or constant 2. Okay. Pre-stitch depending upon you, whether you are taking 1.5, 2, you can play with that. KBB is the frame bending stiffness. You can basically change that bending stiffness as an input. You have to define that. Xi is anisotropy parameter. Again, it's up to you whether you take 0, isotropic case. 1, there is some strength of the reinforcement. 2, higher value if you go, you are basically increasing the strength of reinforcement of the file. So Xi, what are the input parameter you have to give? Xi, proportionality constant, pre-stretch of the membrane, and the frame bending stiffness, as well as the electric voltage. If electric voltage is 0, means you are basically telling about the initial attained equilibrium configuration. When you apply some value of E, there are two possible cases of applying E. Either you supply DC voltage, or you can supply AC voltage, sinusoidal AC voltage, okay, cosine sinusoidal voltage, like cosine voltage, it's up to you. So we are having a different case, E0, EDC or EAC. Get it? Now let's see the MATLAB code. So this equation that we are having, d2 theta by dt square plus kbb theta. So that equation basically, these are the input parameters that I have told you. EDC, let us consider to be 0 first. Okay. Then P here represents the pre-stretch. Let us consider that we start with a pre-stretch of 2. This count you will see in a loop, it will be required. That triple I represent the omega. So for example, if you are supplying sinusoidal voltage, it will be like EAC sin omega t or EAC cos omega t. So omega is what excitation frequency that you are going to supply, angular frequency. So that we have considered initially 1. For equilibrium case and DC case, it is not required. Okay, because voltage is 0. E is 0, then it will not come into picture. B is proportionality constant, beta. Basically beta is here represented by B here. We have some nomenclature here for it. It is 2. H is basically eta, anisotropy parameter. So if you go back to the paper, we will have an anisotropic parameter. From where it comes? It comes from dissipation function. So there is a parameter in the evolution equation. Just go down. Here in the dissipation function, eta is here. You can see eta lambda viscous square dot square. So in this equation, you are having mu beta by eta. What is this? It is a viscosity parameter. So you are having anisotropy parameter, viscosity parameter, okay, and you are having pre-stretch, frame bending stiffness, and electric voltage. So here H is basically eta, viscosity parameter. C represents the anisotropy parameter. Okay, so I hope these are the input we have to give. Anisotropy parameter, proportionality constant, pre-stretch, frame bending stiffness, basically directly we have taken here, kbb theta 0.25. Or the other way you can add kbb here and you can give the value here. That doesn't make any difference. Okay. So, what are the variables? That is an important thing. In this, what are the variables? First thing is theta. Theta is going to, for example, you applied pre-stretch and release. With the time it keep on evolving. Then attain the final configuration. Theta is going to be a variable. Other one is the lambda viscous. Other variable is lambda viscous. The internal variable, that is the viscous stress developed in the membrane, that is also going to vary with the time. We are having two variables, theta and lambda viscous here. If simple dielectric membrane we are considering, what are the variables? Lambda. Lambda and lambda viscous. If you are considering viscoelastic. If not considering, only the lambda is the variable. But in our case, we have converted everything from lambda to theta. So theta is our variable and lambda viscous is our variable. So in MATLAB OD45 solver, with the help of symbolic symbol, SIMS, it represents the symbolic symbol for the variable you define. SIMS represent the symbolic variable. Okay. In our case, let us represent theta by y1t. T means it is going to vary with the time. And by v1t. So it is lambda viscous. So I have given some different name because writing lambda viscous, it's very difficult to write, but it means it will be confusing. So simple, just follow the notation. Y1t means theta t. YV1t means it is lambda viscous t, variation with the t. So notation is clear. P here represent lambda p, pre-stretch. B here is a proportionality constant beta. H is viscosity parameter eta. in the paper. C is the anisotropy parameter, that is xi. Okay. Now symbolic symbol, y1 represents the theta and yv1 represents lambda viscous. Fine. So always the variable you have to, because it is going to vary with the time. You cannot give a value. So you define with the help of a symbol. Sims y1t, yv1t. Okay. Now two equations are there. First is the nonlinear dynamic equation and second equation is evolution equation. Third is the initial condition. So in the V1, let us try to feed equation number 1. First equation, Ankush, just you can show. So that first equation is a very big equation, you can see. Just stop it. Electrical part is also there, minus E square something. Okay, so it's not that much easy. First, every single thing we have write, we taken the printout, we write, it match everything. If you make a single mistake, the equation will not going to solve. Okay, so it's look quite easy now, but it takes a lot of effort and time. Okay, so just Ankush, go to the front page, like front one, V1, V2. So in the equation number 1, the first expression is d2 theta by dt square. Basically, it is the second order derivative of the theta with respect to time. So there is a syntax, we can directly write differentiate y1. y1 is what? Theta. Comma 2. When you write comma 1, it signifies d theta by dt. If you write differentiate y1 comma 2, it means it is d2 theta by dt square. If you write differentiate y1 comma 3, it will be d cube theta by dt cube. So it is like this. So difference order of like that you can directly write like this. Okay. Then we are having plus kbb theta. Okay. So kbb is the frame bending stiffness. We have given us some value initial 0.25. The simplistic thing is you can directly put here kbb. So you can also have the variation of it. Okay. And then we are having kbb theta means y plus 2p. 2p means 2 lambda p square into sine theta by 2. So there is a, like whenever you are using, here basically what we have done, we are converting this OD to the vector field. I will tell you later on. So for if solving that vector field, always put dot. Directly dot put the star. Star means multiplying here. So for example, 2 lambda p sine theta by 2. So when you are putting this thing, so it is 2 lambda p squared dot star. If you directly put sine theta by 2, multiply, MATLAB will not able to solve. So there is some syntax that you have to follow. Okay. So always put dot star when you are multiplying with the variables, something that is going to vary with you. So theta is going to vary, lambda viscous is going to vary. So always put dot in that. Dot star. Direct multiplication don't put. If you put star, it will not able to solve. That is one suggestion. You are basically not going to work on that. Ankush just show equation on V2. So we have feed equation 1, nonlinear dynamic equation of the motion. Second equation is the evolution equation. So that is, if you go back, Ankush just show the paper. Differentiate y viscous 1 comma 1. It is what? D lambda viscous by dt. So this is the equation. D lambda viscous by dt. There is some parameter. So it is again, you can give some value to that parameter. Plus mu beta by eta. Now show the code. So differentiate y viscous comma 1, but it means d lambda viscous by dt, because y v1 is lambda viscous here. Okay. Plus mu beta by eta. So beta is b by h is eta. Okay. Then again the complete evolution. So I will share this. I am not going into detail, but to basic understand how to write the order d2 theta by dt square, d lambda viscous by dt. You can write in this way. Okay. Just go back. Now we have already written two equations, evolution equation and nonlinear dynamic equation of the motion. Okay. Now that I have told you, we are having a very large ordinary differential equation. So MATLAB क्या करता है? MATLAB basically do the multiplication, matrix conversion and do the multiplication like this. So what it do? It basically convert ODE to the vector field. It convert entire ordinary differential equation to the vector field depending upon the input that you have given. So for that, basically, you have to simply convert that. You have to give a command v comma s. So s is in which your solution is going to be stored. V is what are your input equations. So in the V, basically, we are going to have the V1, V2. In V, we have these two equations, V1 and V2. In the S, your solution will be coming. So there is a syntax directly V comma S ODE to vector field. Means convert ordinary differential equation to the vector field where you will store in V comma S. In V, your V1, V2 will come, and in the S, your solution will come. So it's a syntax V comma S ODE to vector field. Kiska solution you want? The solution of V1 comma V2. Two equations. You want the solution of that. You are trying to follow this step by step? Okay. Then there is a simple thing, triple M function, MATLAB function V. That what it is doing basically? It is showing that in V, what is the variation? The variation of with respect to what? So we are having the variation of in V. In V we are having V1, V2. Okay. So in V there is a variation of this Y. So two Y symbols will be there. One is theta t and other one is lambda business. That variation with the t should be stored. So ये आपको remember नहीं करना. It's a syntax, common syntax that we follow, but you have to understand what it is doing basically. Okay. So what is happening in Vs? You have the two equation. In S, solution will become. Getting? And in this, basically, you are showing that the variation of V will be there, and in V you are having theta and lambda viscous. Its variation with t basically. So you have defined. यहाँ पे change क्या होगा? अगर variation with respect to something else, your t will going to change. Your V, if not this function of V1, V2, your it is going to change. Syntax will remain the same. Okay. So now the final thing. You have two equations. You say stored it in V, find the solution and put it in S. Now you have given that the variation is with respect to t. Now apply the command. How to solve that? You have everything with you, equations are there. Now you have to solve that equation. So directly give a command that ODE 45. That's what come into picture. Ordinary differential equation 45 solver now come into picture, solution. And but it has to give mm. In mm you have already stored what? The variation of the V. And in V you are having theta and lambda. So it is now OD 45 mm. Now it will ask, T you have given, the variation is with respect to T. But what is the range? If you see in triple M, you are having the variation of Y with respect to T. But what is the range? So that time you can define. For example, I say I variation initially from time 0 to 300, 500, 600, 10,000, whatever. It's up to me. So I initially define says 300. It's not like that. I have already solved in the paper. I started with 100, 200. So in 100 we see some oscillations coming, but still it's going on. So I increase the time to 200. Then it will be converged. So what we want, initially when your structure will bend, it will attain a configuration, it will stop there. So for a particular time we have to find out. Na? So we keep on changing. Then we have find out that up to 300 we can easily capture the entire behavior. So 0 to 300 will be your time. Now it says for what initial condition. So what are the initial condition? I can tell you. Ankush, just put right click on S here, V comma S right click करो and open करो. Right click करके S को open करो. ये S लिखा है V comma S. उसको select करो S को पहले. हाँ ये open करो.
कमांड विंडो में ऐसे कैसे कर सकते हैं?
So in the solution S, how it is going to see? It's like V comma S. So what are the things it is going to solve? So S you see it is a 3 into 1 symmetry. So the first one is Y viscous one. What is Y viscous one? It is lambda viscous. We have already defined Y viscous one here, it is lambda viscous. Second thing is Y1. Y1 is we have taken, Y1 is what? Theta. And then it will have dy1. Yani d theta by dt. You are getting? So in V we are having the variable, in the S we are going to have the solution for this thing. So we are going to solve in the S these three things. So I have opened you specifically to do this thing. Now you have to give initial condition for all these things. What is Y viscous one initially you are taking? Y1 you have to define. Y viscous one means lambda viscous. y1 means theta and d theta by dt. Already we have considered this initial condition. Just close this. Why I opened this? Because in the solution you define the time space. For 0 to 300 you want the variation of with the time. Initial condition. So what is lambda viscous initially? Lambda p. Lambda viscous is lambda p. So the first one is lambda viscous in the S. Second one is y1, means theta will be there. So that should be initially 0. But if I put initially 0, that MATLAB leave at least some very negligible value to start with the solving. So if you put 0.000001, actually it will start initiating solving. So 0.00001 is nearly tends to 0. If you directly put 0, it will not solve that equation. Okay. Theta is initially 0. You are getting my point? But if you put exactly 0, so all the values that you have put, like everything vanish, so it will not able to solve. So put 0.000, extremely small value. It will be almost 10 to 0. Okay. And what is d theta by dt? Third one, 0. So what is happening in V comma S, we have the variation of y and lambda viscous with respect to what? With respect to time. So whatever you are having variation, you put it in this one. Variation of with respect to time from 0 to 300. You can show the initial time here. This is we have put it. Theta to be 0, d theta by dt to be 0 and lambda viscous to be lambda pre-stretch. But in S, it is solving like lambda viscous first, theta then and d theta by dt. So lambda viscous is lambda p, we put 2, theta is second case 0, 0.00001 and d theta by dt 0. So that we have put in the code. Just show that thing. So I hope up to this point is clear. Doing nothing, define input variables, okay, write the equation and just put that equation solver Vs, your two equation will come and S, your solution will be there. Fine. And then you write the MATLAB OD45 solver command, in which you have to define the variation is with respect to what? What is the range? So I says the time is going to vary. It is going to vary from 0 to 300. Define the initial condition. Define the initial condition for S, because we are considering our V comma S. So we have defined the initial condition. Now you say that directly you can consider some different parameter. You are saying that time is from 0 to 300. But I says ki interval, sub-interval I am also required. Okay. So it will go to 0 to 300 but in very, very small sub-intervals. Like 0, 0.5, 1, 1.5, 2, like this. It not directly go to 0 to 300 but in some interval you want to go. Why? Because for dynamic analysis, capturing the response at the minute point is very, very important. So you have to subdivide the interval. Okay, the variation of the time, with the variation with the time will be there, but it should be in a very small subinterval. So for defining that thing, what we have done, X is lin space. So you can use any symbol. Lin space means linearly spaced. So if I am going from 0 to 300, so there is a syntax, X to lin space 0 to 300, comma this. So this 10,000 is defining how much subinterval you are taking to reach to that. You are getting my point? You are going from 0 to 300, but by following 10,000 sub steps. So when you divide 300 by 10,000, you will get a particular value. So 0, that particular value, 0.0003 plus 0.0006, 0.0009, then you reach to 300. Getting my point? So X is lin space means linearly spaced. Linearly your variation will be there. Okay? This is, you can see. What is X? Okay. So it's a more smaller value you take, like if you take 1 lakh subdivision, you will reach, but computational time will increase. Okay. Just close this. So I will quickly try to wind up by showing you one of the results. So now everything is done. Solution, your equation is being basically solved with the initial condition and two equations. Now you say that let our three things will come into picture. First thing is theta we want. Second is basically we want lambda viscous. Third is d theta by d. It will come. So we say that in y1 d eval, iska matlab hai evaluate. D eval means evaluate the equation, evaluate the solution basically. Solution is representing what? This is the solution. Solution of MMM MMM consists of what? It consists of two equations. If you see, solution consists of OD45 implement to the MMM by using this condition, time, space and the initial condition. So MMM consists of the variation of the V with respect to time, and what V consists of? V consists of two equations, V1 and V2. So we are saying that evaluate this solution, okay, with respect to X. X means now time, because we have divided the time in sub-interval. X is length space 0 to 300 by 10,000 sub-interval, comma 1. The first variable in the solution that you are evaluating will now get stored in Y1. So what is the first variable? Lambda viscous. So again, just open and show them 3 to 1 symmetry of S, otherwise they will get confused. So the first solution stored in Y1. Just show the S value. This one. So S first one is lambda viscous. So we are saying that you solve it. Now in Y1, just store the value of lambda viscous. In second Y2, just store the value of Y1. What is Y1? Y1 is theta. In Y3, just solve it and store the value of d theta by dt. Get it? So just close it. So we have done this Y1, Y2, Y3. Solution with respect to time 1, 2, 3. In one we have provided lambda viscous. In second we have provided theta. In third we have provided d theta by dt. So solution of these two equations along with the initial condition, and finally get stored the value in Y1, Y2, Y3. Just close and push one by Y1, Y2. Close karo. Okay. So now you are having. You are for a particular pre-stage and the defined variable, you are having input that you have defined. You have the answer for that. Now you say that X is defining time interval 0 to 300 with a divide of 0.0003 like this. So I say that first thing is I want the plot of theta with respect to time. Okay. So what you do? You do plot X comma. One thing you can do directly, instead of D equal to Y2 and D1 equal to Y3. So we have stored the value in some or other form, or directly you can use Y1, Y2, Y3. No problem. Okay. So D here, in D Y2 value is being there, and in D1 Y3 value is there. So Y2 value is basically theta. So you say the plot X comma D command. Just go to the top. First show the variable. So plot X comma D, put C equal to 0. Initially we start with the isotropic case. We put anisotropy to be 0. So put C to be 0 and eta to be 5. Viscosity parameter to be 5, then 10, then 50. We are going to change it. 5, just put it 5. Now run the code. So depending upon the compatibility of your system, you will get the result as okay. So this is the figure we obtained. The variation of the theta. No, this one not unused. Close it. One purpose to figure. AC में क्यों सॉल्व करो? DC में करना था। DC में जाओ। इसमें करो सर। C को 0 कर दो। ठीक है? और ठीक है। आगे करो। That AC will EA sin omega t will come into picture. But we are concerning about the initial configuration where EDC EAC 0. इसको बंद कर दो फिगर को. दूसरी फिगर ओवरलैप करेगी. It's a code that have both AC, DC, in which you can solve. Now you can see. This is the first part. X-axis you are having the time interval from 0 to 300. On Y-axis you are having basically theta in radian. Okay, that is for viscosity parameter eta, anisotropy parameter 0. Just minimize this. Change the viscosity parameter. You can see the effect of viscosity parameter. Now find for 10. So always put the hold on command so you can parallelly compare what is happening at 5, 10, 50 like this, okay? So you see at 10 the orange one is being swing. So ultimately you see the structure here is attaining the same angle. For 50 you can also show. So they are attaining the same angle, but when we are considering the viscosity of the system, so you see the time it will taken or to reach the initial equilibrium configuration is varying. That's what we are anticipating. So if the structure will have different viscosity like membrane, so it will take different time to reach to its initial configuration. So this is for 50. Now you can show the paper image. This image exactly you can see we have provided in the paper. This is for anisotropy parameter 0, the top one. Okay. So this one you can see it is for anisotropy parameter 0, means xi is 0 here. So what is happening? What is the conclusion from this? For anisotropy we will put z to be 1, xi to be 1, then we can see. So the conclusion is that when we are considering the viscosity of the membrane into account, okay, without anisotropy, so our structure with the different viscosity parameter ultimately land up to a same attained configuration, but in the case of the membrane with the higher membrane viscoelasticity, the time taken by the structure to reach to that configuration increases. Okay, or we say that in case of the membrane having low viscosity, membrane vibration attenuates very fast. You can say like that, because very less number of vibration for 5, then 10, then 50. So where this viscosity parameter comes 5, 10, 50, it's a standard parameter that is being obtained by matching with the experimental coefficient. Okay. So I have directly taken from the existing literature. So that is one thing, that it is basically time history plot. How your system variable, what is the variable system variable? Theta is going to vary with the time, evolve with the time. So in the code, just one quick show, then we can go ahead. So I will share this code, you can completely replicate my paper. Okay. So the other important thing, if you change the value of C to be 1, you will have 1, 2, 6 anisotropy parameter. You will get that result. So in the plot, Ankush just show D comma D1. In the plot C0 रख लो या 1 कोई plot C0 रख लो. In the plot now we are doing D comma D1. So it means we are plotting theta with d theta by dt. So we are concerning about phase portrait. First is time history we have seen, now we are seeing to phase portrait. प्लॉट में d कॉमा d3 लिखो बस. नहीं नहीं उसी में लिख देना ना, x को d लिख दो और को d3 कर दो d को. ठीक है, तो नीचे लो. होल्ड ऑन कमांड ऊपर चलिए. d2 कॉमा d3 कॉमा d1 d बनाया, d2 d3 नहीं error है. So plot d1. In d we are having theta, having d theta by. So just to show this portrait, keep okay for isotropic and isotropic. So you have a lot of parameters. Vary the flame maintenance, pre-stretch, anisotropy parameters. So you have a complete picture, dynamic and so elastic membrane with minimum. Okay. So in working in some you will directly get easily figure. So this is the face portrait. Is find all this picture with complete explanation in my page. So that is what we are writing. Provide all the details. Sometimes you feel it like most get it. So go, it's down one. This one. So xi 0 you face put. If you put the values, Ankush, you can put the 1. So you can compare and I this is in the extension of the code omega, that is EA sin omega t. When you apply the extension in the sin, you can obtain the difference like point kare map. So we have the code we are Share with you. You can see we are present, we are getting it. Okay. So please go through the paper and the code. If you find any difficulty, I'm still here, or even after going from here, we can discuss it. Is it fine? You understand the basic modeling, experimental fabrication? I have in my PPT for the finite element, but I will continue tomorrow. Otherwise, it will be a long lecture. So thank you very much. So online audience, you have any doubt?
Not yet, sir. Thank you so much, sir.
So I hope you all are able to follow. I will share this paper as well as the code so that you can practice and you can carry forward in your research. You can use this code.
Okay, sir.
Thank you so much. Thank you for joining online. And we will at 1:30 p.m. again have this session. Okay. So please join at that session only.